This week we're going to be doing sections 9.4 and 9.5, beginning with 9.4, properties of logarithms, where we're going to learn some relationships with logarithms that we've already learned with exponential functions, but slightly different. Logarithms, like we taught last week, are related to exponential functions. So that means the relationships that we learned for those exponential functions carry over to logarithmic functions, and there are a lot of similarities. Let's do a little bit of review. Remember how when you take a constant, any constant, and raise it to the 0 power, it will always equal 1. Now remember we introduced last week that when you take the logarithm base a of 1, no matter what the base is, that will always equal 0. Well, the reason for this is if we were to convert this a to the 0 power equals 1 to logarithmic form, remember we're going to write down the logarithm. The base of the exponent is going to become the base of our logarithm. Over here we're going to write an equal sign. It's going to equal to the exponent, which is 0, and the remaining number is just going to go here. That's how we go from one to the other. So our property that anything raised to the 0 power is 1 translated to logarithms to say that the logarithm of 1 is always 0. And we have other relationships for exponents that we've learned that can translate to logarithms as well. So on the exponential side, we had relationships such as x to a power times x to a different power could be rewritten as x plus those two powers, or x raised to the summation of those powers, right? And if we were to take x raised to a power a divided by x raised to a power b, we could combine those x's into 1 and have that raised to the difference of the two powers. And then if we were to have an x raised to a power a raised to a power b, we could just make that the product of the powers. That is x raised to a multiplied by b. We are going to learn some new relationships. The derivation of these relationships can be found in your textbook, I believe. I'm just going to write them so we can learn them before we get into the theory of them, because getting into theory too early can muddy the waters of your understanding. The first one we're going to learn is the product property, and it's going to relate to this one right here. The translation of this property to logarithmic form is when you have the logarithm of any base, it doesn't matter. We're not going to write one because that means by default this is a log base of 10 of a product and another product. This can be rewritten as the logarithm of one of those products plus the logarithm of the other product. That's the product property. We also have something called the quotient property related to this property right here, and that is going to be when we have a logarithm of a quotient, a numerator and a denominator, we can convert it to the logarithm of the numerator minus the logarithm of the denominator. And we're going to introduce one more, and we're going to call it the power property. The power property states that when you have the logarithm of a factor, so let's say factor x, raised to a power, let's say 5, that can be rewritten as that power multiplied by the logarithm of the factor x. So what we've done is we've taken that power and we've put it in front of the logarithm. Now that we've introduced those, we are going to do some practice problems with them. So let's say we had the logarithm base 2, now the base doesn't matter, we're just writing it because, of x divided by 17. If we look over here to our properties, we see that we can apply quotient property to expand this into 2 logarithms. So the way we do that is we take the logarithm of the numerator and subtract the logarithm of the denominator, 17. So that's going to equal the logarithm of x minus the logarithm of 17. Now we can do another example. We're going to do a bunch of these examples just to show you how it works practically. So strap in, get your notepad out. Let's take the log base 2 of the square root of 8. Now, when we look over, we don't immediately see which property we can use. So let's try to reimagine this square root of 8 as in a different form. Well, the square root of 8, anything under a radical sign can also be written as that the radicand raised to the 1/2 power. And now we have a power property. So we can rewrite this, that's a terrible equal sign. We can rewrite this as 1/2 times the log base 2 of 8. And we could perhaps leave it there. However, we could try to simplify this further by saying that 8 is the same as 2 cubed. So let's write it as 1/2 times the logarithm base 2 of 2 cubed. Well, now we can use our power property again. So we are going to take this 3 and bring it to the front of the equation. That's going to give us 3 over 2 multiplied by the logarithm base 2 of 2. And now you might remember from the last lecture that when we have the logarithm of a base, the logarithm of a factor of a base, and the base and the factor are equal, that is just going to equal 1. So this doesn't mean it cancels out completely, that just means it goes to 1. So then our final answer, our final simplification, is just going to be 3 over 2. Now, let's do a little bit more complicated. Let's say we had the natural logarithm, ln, of 3x squared divided by y. Well, first we see that we can use the quotient property, so let's do that. Let's take ln of the numerator minus ln of the denominator y, but we're not totally done yet. We can also use the power property on this part, so let's expand that. This can then look like, let's see, let's take it back a little bit actually. Before we can use the power property, see, the only thing being raised to the second power here is the x, not the 3. But we could use the product property on this 3x squared to separate the 3 from the x squared. And if we do that, the product property is going to give us the natural log of 3 plus the natural log of x squared minus our ln y. And now that we have x squared by itself, we can use the power property to simplify this further and say that the natural log of 3, or say that this term over here can be expanded into the natural log of 3 plus 2 times the natural log of x minus the natural log of y. I'm going to make some space on our board by deleting these old problems. Go ahead and pause the video and write this one down if you have not finished doing that yet, because I'm going to erase it. And we're going to move on to some more examples. And now we're going to start getting into some warnings and things to avoid if you don't want to make mistakes in your homework. So let's say we were taking the natural log of y multiplied by a polynomial y minus 1 squared. There's a little multiplication symbol here. Well, first we can use our product property because we have the product of y and y minus 1. So we're going to separate that by taking the natural log of y plus the natural log of the quantity y minus 1 squared. Now the entire factor of this natural log is being raised to the second power, so that means we can use the power property to simplify it further, or to expand it further. So our ln(y) is going to drop down, and we're going to add to that 2 times the natural logarithm of y minus 1. And now we can look for ways to simplify it further, and we don't have any. This is I keep saying simplify, I mean to say expand. This is the expanded form of this logarithm. This is the final expansion of the original logarithm. Now you may be tempted to see this polynomial, y minus 1, as a thing that can be distributed. However, the factor of a logarithm cannot be distributed. So this ln of y minus 1 does not equal, so let's write it here, ln of y minus 1 does not equal the ln of y minus the ln of 1. There is no distributive property that you can use with the natural log, just like we can't distribute something like the square root of y minus 1 into the square root of y minus the square root of 1. We can't do that because there's no distributive property here, which means our fully expanded form is just the natural log of y plus 2 times the natural log of the polynomial y minus 1. Now, another warning that I'm going to give you is that let's say we had the natural log of x divided by the natural log of 5. We might be tempted to use the quotient property, but see here that we do not have the natural log of x over 5. We have the natural log of x divided by the natural log of 5. These two terms are not equivalent. So don't try to use the quotient property with them. Now let's work in reverse. Let's take some already expanded logarithms and let's combine them into one term. So let's start with an easy one. Let's say we had the logarithm of 4 minus the logarithm of x. We want to expand this into one term. We look over here and we see that when we have two logarithms being subtracted from one another, we can use the quotient property to turn that into the logarithm of the first factor becoming the numerator and the second factor becoming the denominator. And this is our final answer. Let's do another. This one is going to be more complicated, probably the most complicated thing we've done this lecture yet, but don't worry. we're going to take, we're not looking at that anymore. We're going to take 4 times the natural log of 3, and we're going to subtract from that 2 times the natural log of x, and we're going to subtract from that the natural log of y. What are we going to do first? Well, first we might want to use the power property while these are by themselves. Before we combine them with any other logarithms, we are going to use the power property to transform this term and this term. So by the power property, we can say that the first term becomes the natural logarithm of 3 raised to the power of 4 subtracted by the natural logarithm of x squared minus the natural logarithm of y. So let's see what else we can do. We have 2 minus signs here, and if we have these 2 minus signs, we can pull out a negative sign and just rewrite this expression as the natural log of 3 to the 4th minus the quantity of the natural log of x plus the natural log of y. And now that we've done that, we can use the product property to combine these two terms. So we're going to write that the natural log of 3 to the 4th minus our new natural log of x squared multiplied by y. And now we can combine these one more time using the quotient property. We wanted to use the product property before the quotient property just because that makes it turn out a bit more smoothly. It would result the same way either way, but this way is a bit easier to work with. We're going to use the quotient property to finish off this problem by saying that the natural log, or these two terms, combine into the natural log of the first factor becoming the numerator and the second factor becoming the denominator. We could expand this 3 to the 4th if we wanted to. We're not going to because it doesn't really matter. The final answer is going to be the natural logarithm of 3 raised to the 4th divided by the quantity x squared times y. So now let's talk about the strategy that we can use to approach condensing logarithms, because it can be kind of tough sometimes. It can be tough to figure out where to begin. Let's say we had a problem similar to what we just did, the logarithm of 3 minus the logarithm of 5 minus log of x. And we want to know what is the best way, the simplest way of going about this. Well, I would recommend that you always start with the power property. So we'll do that here. We'll look through and see if we can use the power property at all. The coefficient of log 3 is 1, the coefficient of log 5 is also 1, and the same with log x. So we can't use the power property here. So we'll move on to the product and quotient properties. Now, these can be done in any order to get to the same answer. One way might be easier than the other, but you can do either. You can also, we can do a little trick where we do both at the same time, and it gets us to our answer faster. So previously what we might have done is we would have pulled out this -1 and put these in parentheses and made that positive. But instead, let's just say that using both at the same time, any positive logarithm Now that we can no longer use the power property, any positive logarithm is the factor of it is going to end up in the numerator, and any negative logarithm, the factor of it is going to end up in our denominator. So doing that, let's write the logarithm, and we'll draw a little division bar here, and we'll pick out all of our positive factors. So we have a positive log 3, and that's the only positive factor that we have, so we're going to put it on top. And now we have a negative log 5, so we're going to put that as a factor in the bottom. We have a negative log x, so we can put that as a factor in the bottom. And now we have combined steps to arrive to an answer faster. And if we had done this the other way, if we had rewritten this as minus the log 5 plus log x, we would use the product property to turn this into log 3 minus log 5x. Then we would have used the quotient property to get the log log 3 over 5x. So we arrive at the same answer. Just one way, we're combining steps to get there faster. Now, whoops. Yeah, that's right. What if, let's try a different kind of problem. Let's say that we are given that the value of, now this is going to be hard to type, so I'm going to have to write it, that the value of log base 5 of 2 was 0.431, and that the value of log base 5 of 3, that's supposed to be a 5, was equal to 0.683. And then we were asked, what is required of us is that we evaluate log base 5 of 6. Now, we could use our calculator, and the way we would use our calculator, remember, is taking the log base 10, or just simply the logarithm on the calculator of 6 divided by the log base 10 of 5. We learned that last week. And then evaluating that on the calculator, we would get an answer of 1.113, and then it could carry on to 2.8. We could truncate it to 3, or round to 3. But we could also use our properties to write this in a different way. So to do that, we can recognize that 6 is the product of 2 and 3. So let's write this as the log base 5 of 2 multiplied by 3. And now that we have that, we can use our product property to split this up. So we can write this as log base 5 of 2 plus the log base 5 of 3. And we're given the values of log base 5 of 2 and log base 5 of 3. So we can plug those values in. This is going to be 0.431 plus 0.683. And then adding those together, we get 1.114. And these answers are just about equivalent. Now, this answer is slightly larger, but that could be due to some rounding error. So these answers are the same. We can get there either way. So let's say you just happen to not have a calculator on you. It's a rare occurrence in this day and age where we have cell phones with calculators on them. But let's say you didn't, and you had to evaluate log base 5 of 6 given these. This isn't a realistic scenario, but you can do it. It's possible. Now let's do this again, this time using the same values, but let's say we had the log base 5 of 9 over 2. Well, we can evaluate this as well. But first we have to recognize that we can use the quotient property on this. That's going to give us the log base 5 of the numerator minus the log base 5 of the denominator. So we have one piece of our problem. Now we have to recognize that 9 is a perfect square. 9 is 3 squared. So we can rewrite this further as the log base 5 of 3 squared minus the log base 5 of 2. And now we can use our power property to take this exponential 2 and put it in the front. That's going to give us the log base 5 of 3, 2 times the log base 5 of 3 times the log base 5 of 2. And now we can plug in our values and write an equation of 2 times 0.683 minus 0.431, and evaluating that, our answer is 0.935. So why is learning any of this important? We're in the next chapter, 9.5, we're going to start learning how to solve logarithmic and exponential functions. But let's give a little sneak peek into that. Let's say we were given the exponential function 2x is equal to 5. Now, previously, we didn't know where to go with this. We were done. We couldn't solve this any further. Now, we know that we can convert this into logarithmic form and try to solve that way. However, instead of doing that, what if we just recognized that logarithm is an operation just like any other, and if we do the same operation on both sides of the equation, the equation remains equal. So what if we took the logarithm, now this is base 10, but we're not going to write it because it's understood, the logarithm of 2 raised to the x, and set that equal to the logarithm of 5. These two are still equivalent. Now we can use the power property of logarithm of 2 to the x and write that as x times the logarithm of 2 is equal to the logarithm of 5. Well, the logarithm of 2 is just a number. It's an irrational number. And the logarithm of 5 is just another number. So we can use a little bit of algebra and divide both sides of the equation by the logarithm of 2. And that would isolate our x term and get us to solve for x. So we can write this as the log base 10 of 5 divided by the log base 10 of 2, and now we can evaluate that with our calculator. So this is why learning logarithms is important. This is a common scenario in math to have a variable exponent, and we wouldn't have any way to solve for it without using logarithms. Now we're going to begin with lesson 9.5, which is solving exponential and logarithmic equations. We're going to take the tools that we've learned and we're going to apply it to different equations of varying difficulty. And I want to remind you of an old trick that we learned for solving exponential equations. So previously we could take something like 4 raised to the x plus 2 power equal to 64, and we could set the bases, or we could make the bases equivalent to each other and then set the exponents equal. So in this case, we could rewrite 64 as 4 cubed. That would give us 4 raised to the x plus 2 is equal to 4 cubed. Setting our exponents equal to each other, that's x plus 2 equals 3, meaning that x can be solved as 1. And this works sometimes, but it can't always be used. So let's say, very similar to the example we did at the end of last lecture, we had x raised to the power of x, or 2 raised to the x power is equal to 7. If we try to use that old trick, well, there's no way that we can make the bases common. We can't transform 7 into 2 with any exponent business or anything like that. So we can't use our old trick. But we learned some new things where we could take the logarithm of both sides. So that looked like log base 10 of 2x equal to a log of 7. And remember, we can use the power property to write that x times the log of 2 is equal to the log of 7. And then, since log 2 and log 7 are just numbers, we could solve for x and say that x is equal to log of 7 divided by log of 2. And this could be evaluated. It happens to be equal to 2.807. So we're going to spend some time today solving equations like this, and we're hopefully going to develop a feel for how it ought to be done. So let's erase what's on the board. Let's say we have a problem where we have logarithm on both sides already. And this is where we begin. We have a log base 5 of 2x, and that's equal to a log base 5 of 36. Now, you might want to begin by using the product property or even the power property by turning this into 6 squared. But first, if we think of logarithm as a, what's it called? Not function, maybe a function. Logarithm as a operation. If we think of logarithm as an operation, then we see we have the same operation happening on both sides. So we can have these cancel. And that would leave us with 2x is equal to 36. And this is something that we can solve very easily. X in this case is going to equal 18. We were able to do that because we had the same logarithmic operation on both sides, and they had the same base. That is a very important factor, is if this were the logarithm of 5 and this were the logarithm of 6, we couldn't cancel them out so easily. Now let's say we had an operation where the logarithm was only on one side. Log base 6 of 4x is equal to 2. And we want to figure out the best way of solving this. Well, we could, this is a 6, I apologize. I suppose we could try to use the product property somehow, but that's going to leave us with a log x, which we may not know what to do with. But since we only have a logarithm on one side, it may be a good idea to convert this back to exponential form. And as we see, whatever a logarithm is equal to, that's going to be the exponent. Since our exponent is 2, this may be easy to do to evaluate as an exponential form. So let's convert it. So our base is 6, so we're going to write 6. Our exponent is 2, we're going to write a 2. And then we're going to set it equal to whatever is left over, and that is 4x. And now we can solve this. So evaluating this can be, we can turn 6 squared into 36, yeah, 36. Divide both sides by 4, and that gives us x is equal to 9. And as a general rule, whenever you see logarithm on one side of the equation and it's equal to a constant, not a variable, it can easily be transferred into a exponential function. So now let's do another. If we had 9 raised to the x plus 2 power, and we set that equal to 1 over 27, we want to figure out the best way to solve this. Now we could try to convert these into logarithms, and that might work, but before we do that, we can notice that the base of both of these sides, this is 1 over 27 raised to the 1 power effectively, the bases have a common factor of 3, which means we might be able to make the bases common. So let's try that. 9 can be rewritten as 3 squared, so we'll have 3 squared raised to the x plus 2 power. And we're going to set that equal to 1 over 27 is a perfect cube that can be rewritten as 3 cubed. Now we can use some of our properties and simplify. So a power raised to another power, we can multiply those exponents out to be 3 raised to the 2x plus 4 power, and set that equal to, we have another property where if we have a exponent in our denominator, we can bring this to the top while making our exponent negative. And now we have common bases that we can set equal to each other. So we can say that 2x plus 4 is going to equal negative 3. If we add 4 to both sides, that's going to be 2x is equal to negative 7. Dividing by 2, x is going to equal negative 7 over 2. Now let's do another example. And if I'm erasing too fast, you can just pause the video and write everything down and then move forward. Let's have 4 raised to the x minus 3 power is equal to 9. Now first we're going to look, can we make common bases? No, we cannot, but we can try to take the logarithm of both sides. So let's do that. Let's have the logarithm of 4 raised to the x minus 3 power, and then take the logarithm of the other side, that's the logarithm of 9. Now we can use our power property to bring this polynomial at the top to be the, what's it called, the, I cannot remember the term for it, what's in front of a factor. We're turning it into a factor, multiplying it by the logarithm of 4, and that's going to be equal to the logarithm of 9. And now, since the logarithm of 4 is just a number, we can divide both sides of the equation by it. And that's going to give us that x minus 3 is equal to the logarithm of 9 divided by the logarithm of 4. And to isolate x by itself, we can just add 3 to both sides of the equation, giving us that the logarithm of 9 divided by the logarithm of 4 plus 3 is equal to x. Now, let's say we had this same expression, this same equation, but we were given something like 5 times 4 raised to the x minus 3 power. Well, we would want to get the exponential by itself before we did the logarithm of both sides, because that makes it simpler for us. And we can do that. We can divide both sides by 5. If we had something like 5 plus 4 raised to the x minus 3 power, we would subtract both sides by 5 because we want to get this term by itself before we take the logarithm of both sides. That's going to make solving our equation easier. So let's practice that. If we have 2 times e, remember e, Euler's number, raised to the x equal to 10. What are we going to do first to solve this? Well, we want to get this, the factor with the exponent by itself. So we're going to first divide both sides by 2, and that's going to give us e to the x is equal to 5. And now e to the x is by itself, and we can do something. We can convert this, or we can use the logarithms to help us solve this. Now, since we're using e, remember that the natural log uses a base of e, so we might want to go ahead and use the natural log anytime that we see an e in our equation. So let's take the natural log of both sides of the equation. That is going to give us the natural log of e to the x is equal to the natural log of 5. Let's use the power property and bring that x to the front. Now we have the natural log of e is equal to the natural log of 5. Remember, natural log is to a base of e, and since in this case we have a factor and a base are equal, that's going to simplify to just 1, which means now we have x equal to the natural log of 5. And that is our final answer. We can use the calculate to evaluate the natural log of 5 to get an answer for x. Let's do another example where we bump up the complexity just a little bit. Let's say we had 5 plus 2 times e to the 2x plus 1 power, and we set that equal to 115. First, we're going to get this term by itself to make it easier to solve, and we're going to begin by subtracting 5 from both sides and then dividing both sides by 2. I'll do those steps one at a time. We're going to have 2e to the 2x minus 1 is equal to 110 because we've subtracted from 5 from both sides. Now we're going to divide this 2 by both sides of the equation. That's going to leave us with e to the x minus 1 is equal to 55. And now that we are at this stage in the equation, we can take the natural logarithm of both sides. We're going to use the natural logarithm because e is involved. So let's do that. The natural logarithm of e to the 2x minus 1 is going to equal the natural logarithm of 55. Now we're going to use the power property to bring this 2x to the minus 1 to the front. 2x minus 1 times the natural logarithm of e. Remember, our base is e, so that's just going to turn into 1. So I'm not going to write it down again. Is going to equal to the natural log of 55. And now what we have is a number and a number. We can solve for x. So first we're going to add 1 to both sides of the equation. Then we're going to divide by 2. And I know you guys can do that, so I'm just going to write it out. We're going to have the natural log of 55 plus 1, whole thing, divided by 2. And we can use a calculator to evaluate that. Did I make a mistake? Oh, well, this was supposed to be plus 1. That was how I wrote my example down, but it doesn't matter. We got to the same answer, as well as in, like, we still did the process correct, whether this was plus 1 or minus 1. That would have just changed our answer over here to be minus 1 instead of plus. So that's my mistake for reading my notes wrong, but we did the correct process there. Now let's do some more. Let's see. Okay. Let's say we have 2 multiplied by the logarithm base 4 of x is equal to 5. First thing we want to do is we want to get the logarithm term by itself, so we're going to divide by 2. That's going to give us the logarithm base 4 of x is equal to 5 over 2. And now that we're here, where do we want to go? Well, let's see. We have logarithm on one side only, and this side that represents the exponent is just it's a whole number, it's a constant, so we don't have a variable involved, so we can convert this to exponential form. We're going to have a base of 4, remember, because the base of our logarithm is 4, The exponent is going to be 5 over 2. That's going to equal the other number, which is x. Now, we can evaluate this by hand. This is the same thing as 4 raised to the 5th power multiplied by 1 over 2. Now 4 raised to the 1 over 2 power is the same thing as the square root of 4 raised to the 5th equals x. Now the square root of 4 is just 2 raised to the 5th equals x. Then 2 raised to the 5th is 32. Let's do another. This time we're going to use some of our other properties that we've been neglecting for a little bit. We're going to take the natural logarithm of 2 plus the natural logarithm of x and have that equal to 3. Now, we want to get to a single logarithm term with x in it. We have a second logarithm term. What we could do is evaluate this and subtract it from 3, but instead, let's use the product property to combine these into one term. So let's combine them with the product property. That's going to give us the natural logarithm of 2x is equal to 3. Now we can convert this to exponential form. Remember, our base of the natural log is e. That exponent that's going to go with it is 3. So we're going to have e cubed is equal to the remaining number 2x. Now to solve for x, we would just divide both sides of the equation by 2 and get e cubed divided by 2. And we can evaluate that with a calculator, no problem. We learned how to do that in the last lecture. Let's do one more problem involving a polynomial and a logarithm. So let's say we had the logarithm of x plus log of x minus 3 is equal to 1. Now the first thing we want to do is combine these, and we're going to use the product property to do that. So let's use the product property and get the logarithm of x times x minus 3 is equal to 1. Now that we have the logarithm on one side and a constant exponent, we will remember this is a logarithm base 10. We're going to take 10, raise it to the 1 power, and set it equal to the remaining number, x times x minus 3. My board is acting kind of slow and not recording all my movements. Now we can solve for x, but when we do that, we're going to begin by distributing this x into this quantity right here and moving 10 to the other side. And doing that, we are going to get a polynomial of x squared minus 3x minus 10 equals 0. All we did there was distribute the x through, then subtract this 10 to the 1 power, which is simply 10. Now to solve for x, we just have to factor. The factors available for 10 are 1 and 10 and 2 and 5. So let's write down what we know. We know that we're going to have two quantities that involve x. Since these two signs are negative, the only way for this to be negative and for this to be negative is to have a negative and positive. 1 and 10 we cannot add together to equal 3, so we're going to try 5 and 2 instead. And if we take a negative 5 and add a positive 2, we'll get the factors x minus 5 and x plus 2 can be FOILed into x squared minus 3x minus 10. We could have also used the quadratic formula to get to an answer, but our answer now with this equaling 0 is going to be x is equal to positive 5 and negative 2. Now we need to check that both of these answers are valid. Remember, whenever we involve x squared, square root, whatever, our answers that we arrive to aren't always within the domain of reality. So we need to go back and check when we plug 5 in, that's going to give us the logarithm of 5. That's a real number. The logarithm of x minus 3, that's 5 minus 3 of 2. The logarithm of 2 is a real number, so that is a valid solution. But when we take the logarithm of a negative number, we no longer are working with a real number. The logarithm of negative 2 does not exist, so it fails this. And also, if we were to take negative 2 minus 3, that's the logarithm of negative 5, that also does not exist. And I'm not sure if we've explained why yet, so let's do that. Let's say we took the logarithm of negative 5 and set that equal to x. This is the log base 10. If we convert that to exponential form, we're going to have the base of 10 raised to a power of x equal to negative 5. And if we think about it, there is no number that we could make x that would result in negative 5. There is no number we could raise 10 to get a negative 5. If we had a positive number here, then 10 would just get very large. If we had a negative number here, then 10 would get very small, but it would never be negative, right? You could play around with your calculator on that. If you were to take 10 to the negative 100 power, you're just going to get a very, very, very small number. So that means this x can, it means, yeah, this can never happen. 10 raised to the x power can never be negative, which means a logarithm of a negative number is not real. It's not possible. It can never happen. So this solution of negative 2 is not a valid solution, meaning our only solution is 5. That's all the problems I want to do for today's lesson, 9.4 and 9.5. Now I'm going to give you the homework. Let's go ahead and clear this. The homework for today, 9.4, or for this week, 9.4, is going to be the even problems through 60. And the homework for 9.5 is going to be the even problems through 52. All right, that is all for this week's lesson. I will see you next week.